Hello there. Today we're going to practice the first derivative test. So you just have to recall what a derivative does. A derivative measures a rate of change. So if you recall back to our velocity work, if v of t is positive, then velocity is increasing. So the particle is moving forward. So particle's increasing. If v of t is negative, then your particle is decreasing. If we think of that in terms of a graph, if this is time and this is position, this is the point at which v of t equals 0. And the reason v of t equals 0 is because there is a horizontal tangent line there. Let's just pretend that's a straight line. So v of t equals 0 at that spot, which means before that point, v of t is positive, and after that point, v of t is negative. And the reason v of t is positive there is because the tangent lines leading up to that point is positive, and the tangent lines after that point are negative. So the slope of the graph is positive until it gets to this point where the slope of the tangent line is 0, and then the slope of the tangent line is negative after that point. So what that says is that the first derivative will tell you whether a function, whether it's the position function or what, is increasing, decreasing, or it has a local max or a local min. So the first derivative test helps you find what's called critical points. A critical point is any point which satisfies, I forgot a word there, any point which satisfies f prime of x equals 0. And that just means the derivative is 0. So I'll be more specific, not just f prime of x, I'm sorry, f prime of c. Then c is a critical point. So if f prime of c equals 0, that means there is a horizontal tangent line there. So that could be like this, horizontal tangent. It can be like that, horizontal tangent. Just pretend that's touching there. Or it could even be like that, horizontal tangent line. So it's any point where the tangent line is horizontal, where the slope is 0 at that specific point. So this here would be called a local max. This here would be called a local min, and we'll wait to describe that point. But for now, local max and local min. So you can have what's called local extreme values. So a local extreme value is either a max or a min or end point. Now an end point doesn't necessarily mean that it's a critical point. It may be a critical point, but an endpoint would be a local max or a local min because it would be greater than all neighboring points or less than all neighboring points. So I'm going to draw a graph, and we're going to just identify what it looks like to have a local max, a local min, or endpoints. So let's say we have a graph of a function which looks like that. Let's call this point A. Let's call this point B. So the critical points in this case would be here, here, and here. Those are all critical points because that's where there would be a horizontal tangent line. we have a local max here, a local min there, a local max there, and now let's take a look at the endpoints and describe it as a local max or a local min. Well, here's my endpoint, and it is lower than all neighboring values. So this is a local min. Although it's not a critical point, I don't have enough information to determine if it is a critical point or not. I would have to have more information to the left of this point to determine if it comes back up there. Same as here. This is a local min because all neighboring points are greater than that point. In addition to local extreme values, there are also absolute extreme values. Well, absolute extreme values, or absolute extrema, just to pluralize, so we don't have to say values, absolute extrema, are the greatest or lowest points in a given interval. So in this case, not only is this a local max, it's also an absolute max for the interval AB. This is not only a local min, it's also the absolute min for the given interval. So now the first derivative helps us determine all these points. So an example would be, find the absolute max on 1, 3, 4. I'm going to open up that interval a little bit, give us some other numbers to work with. On the interval 1, 5 for, I don't know, f of x equals 3x to the third minus 2x. I don't know, just making something up here. So, candidates for an absolute extreme, singular, are critical points and endpoints. So let's find the critical points. F prime of x equals 9x squared minus 2. This was a poor example, but hey, not everything works out well in this world, does it? So we'll set this equal to 0. 9x squared equals 2. X squared equals 2 over 9. X equals positive, negative, radical 2 over 3. So these are the critical points. So we are going to test this point and the endpoints. I'm going to neglect the negative because we only care about the interval 1, 5. I'm going to test this and these into our function to determine what the greatest value is. So what we want is f of 1, f of radical 2 over 3, and f of 5. And depending on if this is open or closed calculator section, we may have to do this by hand. So f of 1 is 3 minus 2, which is 1. F of radical 2 over 3 is, let's see, radical 2 to the third is 2 times radical 2, which is 2 radical 2. So 3 times 2 radical 2 is 6 radical 2 over, and 3 to the third is 27. Minus 2 radical 2 over 3. Alright, so I'll just multiply this by 9 over 9 and get 6 radical 2 over 27 minus 18 radical 2 over 27. And forget this value, it's negative. So whatever number that turns out to be, it's definitely not going to be an absolute max because it's negative. 6 minus 18 is negative 12. So f of radical 2 over 3 is less than 0. So I can exclude that as a candidate. So f of 5 now is 5 to the third is 25 times 5, which is 125, minus 2 times 5, which is 10. And this is definitely going to be absolute max. We have 375 minus 10, which is 365. So here is our absolute max because its function value is the greatest. Although we took the derivative to identify a candidate, when we're talking about absolute extreme values, we're talking about the function value. Let's do one more quick thing. Let's identify some increasing and decreasing intervals. So the only candidate at which a function can change direction is after a critical point. So just to draw some graph here, this function is increasing until it reaches that point, and then it begins decreasing until it reaches that point, and then it begins to increase until it reaches that point, and then it decreases until it reaches another critical point. So these are all where f prime of c equals 0. So in order to determine if a function is increasing or decreasing, a function is increasing if f prime of c is positive. It's decreasing if f prime c is negative. And again, going back to that first example we worked on, because the tangent lines are positive, that means the derivative is positive. That means the function is increasing. Because the tangent lines are negative, that means the derivative is negative, which means the slope is negative, which means the function is decreasing. So let's determine some increasing and decreasing intervals for f of x equals x to the third plus 3x squared. So f prime of x equals 3x squared plus 6x. Much better example. I should have used this the last time. But hey, again, not everything works out nicely. So we're looking for the critical points because those will be the only chances where a function can change from increasing to decreasing or from decreasing to increasing. So let's set this equal to 0. Set the derivative equal to 0 to find the critical points. And we have the GCF of 3x, leaving us with x plus 2. So we get critical points of x equals 0 and x equals negative 2. So now, these are the only candidates where this graph can change direction. So what I'm going to do, I'm going to create a rise, fall pattern. Negative 2 comes before 0. And now what I'm doing is creating intervals that are broken up by my critical points. So now I have 3 different intervals for a difference in function behavior. Let's list the factors of our derivative just to make it easier to multiply signs together. And then after I multiply those signs together, that'll be the sign of f prime. So now you could plug it into your derivative. A number to the left of negative 2, let's plug in negative 3. We could plug it into our whole derivative, but the only thing is the derivative could be a little difficult to work with. So let's just multiply the factors together. So now what I'm going to do is choose a number to the left of negative 2 and plug it into both of these factors of the derivative. I'm going to multiply those signs together, and that will be the sign of f prime. So negative 3 times 3 is a negative number. Negative 3 plus 2 is also a negative number. A negative times a negative is a positive, which means the function is increasing on this interval. Now let's plug in a number between negative 2 and 0. Let's plug in negative 1. 3 times -1 is a negative number. -1 plus 2 is a positive number. And a negative times a positive is a negative, which means this interval has f decreasing. And now I can identify -2 as a local max. Okay, now we'll plug in a number to the right of 0. Let's plug in 1. Again, we're plugging into the factors of the derivative. 3 times 1 is a positive number. 1 plus 2 is a positive number. And a positive times a positive is a positive, which makes the function increasing on this interval. And now I can identify 0 as a local min. So if I wanted to list the intervals for which f is increasing, f is increasing on the interval -infinity to -2 and union 0 to infinity. So again, a derivative doesn't necessarily have to be just the graph, it can be the velocity. So the particle could be moving forwards or up on these intervals. So just remember what a derivative stands for. It just doesn't have to be function behavior. The function is decreasing on the interval -2, 0. I'm not including any of these endpoints because negative infinity is not a number at all. -2 is not increasing or decreasing. 0 is not increasing or decreasing. Infinity is not even a number. And it's not increasing nor decreasing at -2 and 0 because the derivative is 0 there.